In this video, I explain MotionAGFormer for enhancing 3D man pose estimation with the Transformer-GCNFormer network from Soroush, Mehraban, Vida, Adeli, and Babak Taati. The paper MetaFormer is actually what you need for vision from CVPR 2022 proposes an idea that says we can consider Transformer as having two main blocks. One of them is attention, which is responsible for mixing the information among tokens, followed by channel MLP, which is applied on each token separately, and by mixing the information among tokens, it can generate a better representation. And there have been some attempts like MLP-like models that they replace attention with spatial MLP. But in MetaFormer paper, they propose MetaFormer as a general architecture, and they say as long as you have a token mixture module that mixes information among tokens, it is likely to generate a model that performs very good. And to prove that idea, they proposed an embarrassingly simple module, as they say, which is PoolFormer. But here in this paper, followed by that idea, we are proposing GCNFormer as a module that can be applied in parallel with transformers. Because since attention mixes the information among all the tokens, but GCN mixes the information in local neighborhood, they can extract complementary information that can be helpful for the task of 3D man pose estimation. The proposed MotionAGFormer receives a 2D pose sequence as the input, which is a tensor with shape t as the number of frames, j as the number of joints, which is 17 in our case, and 3 as x, y, and consensus score. Then they are passed to a fully connected layer, which maps these three-dimensional vectors into a d-dimensional vector. And then after applying a spatial position embedding, we have AGFormer blocks, which we repeat them n times. In AGFormer block, we have two streams. In one stream, we are using GCNFormers, and the other stream, we are using transformers. And similar to previous approaches, we are having spatial modules at first. And spatial MetaFormer in general receives different key points of the human body as different tokens. And what about different frames? They are considered as different batch of data. So spatial MetaFormer is responsible for extracting intra-frame relationship between joints. And followed by these spatial modules, we reshape the tokens so that each token represents a single frame now, and then we apply temporal MetaFormer modules, which they are responsible for extracting inter-frame relationship in the sequence. And finally, we need to merge them. And for merging a strategy, we use adaptive fusion, which is the same as what MotionBird paper from ICCB 2023 uses. It is a weighted average between these two representations, but these weights are unique per each sequence, and the way that it is computed is by applying this formula. The representations from these two streams are concatenated and then multiplied by a W module, which is learned throughout training, and finally a softmax to have a value between 0 and 1 for these weights. And after repeating this AGFormer module n times, we pass them to a fully connected layer, which changes the dimension of channels from D to D prime, and finally a regression head for outputting XYZ for each joint and each frame. Note that spatial position embedding that we added at first is not very necessary because the GCNFormer stream can preserve both the spatial and temporal ordering of the sequence. But based on trial and error, adding this spatial position embedding helps to achieve a better final performance. And finally, what is remained is about how the adjacency matrix in GCNFormers, both the spatial and temporals, are constructed. For the spatial GCNFormer, the adjacency matrix is constructed based on physically connected edges. Like elbow is always connected to shoulder and wrist, or knee is always connected to hip and ankle. We also have tried other type of adjacency matrices like the way that CTR-GCN uses it, but it didn't work as good as having a simple adjacency matrix. And for the temporal GCNFormer, we need to connect a single joint over different time frames. And a naive solution is just to connect one joint to itself in the previous frame and the next frame. But a better solution is to take the similarity of the joint between itself at current time frame and all other time frames and decide the edges based on the similarity. So let's just give you an example for better understanding it. We do it for each key point separately, But here, let's just say we are doing it only for the left wrist and right ankle. And also, let's just say for the sake of demonstration, we have a matrix similarity like this, which are different for each key point. And in our example, it's a 3x3 matrix because we are having only 3 frames, and the row 0 represents time 0. As you can see, in this imaginary example, it is most similar to time 2. And the next row is for time 1, that in our imaginary example, it is most similar to time 2 again. But for the time 2, it is most similar to time 1, because it is symmetric matrix. And we do K and N for each row just to pick the most similar ones. And by assigning K to be 1, we turn the matrix to be like this, and we consider it as our adjacency matrix that says connect a directed edge from time 0 to time 2, because the first row is connected to the last column. And also connect a directed edge from time 1 to time 2, because the middle row is also connected to the last column. And also connect a directed edge from time 2 to time 0, because the last row is connected to the first column. And we can do the exact same thing for right ankle, and that would be like this. And we do it for all other key points separately. Note that another alternative for temporal is using multi-skill TCN instead of this temporal GCN. We have tried it, but it is not as effective of having this module. And about MotionAGFormer variants, we are proposing 4 different variants which can be chosen based on a speed accuracy trade-off. The difference is about the number of AGFormer blocks, the channel dimension, and the number of frames, which end up giving us different number of parameters and different number of multiplication and accumulation. But comparing the result on human 3.6M dataset, when it is not pre-trained on any additional data, we can see that MotionAGFormer achieves better P1 error or mean per joint position error compared to other recent models. And at the same time, it is having less parameters and less multiplication and accumulation operations. Note that second column CE stands for center estimation, and those models receive the whole sequence as the input, but they only output for the middle frame. So the whole model is fast, but if you want to compare multiplication and accumulation for each output frame, they're actually requiring more computation. And I think the reason why we need such models are for real-time processing, that we receive 1 frame at a time and we want to estimate the output. But for the batch processing, that we receive the whole video as the input and we want to see how fast it performs, then the models that the outputs the whole sequence are preferred. And the last column is P1 error in case that 2D estimation that we receive as the input does not have any noise, as the ground truth noise that we have on a human 3.6M dataset by projecting those 3D coordinates into 2D using the camera projection. And in that case, MotionAGFormer large achieves 17.3 millimeters error, which is the state-of-the-art performance. On MPI INF3D HP dataset, for all small base and large variants, we are using 81 frames instead of 243, because the videos in this dataset are usually shorter in sequence, and followed by previous works, we also use 81 as the number of frames. And comparing different metrics, we can see that on mean per joint position error, we are getting state-of-the-art performance, and also on AUC. But on PCK, which is the percentage of correct key points, on 150 millimeters interval, we cannot get as good as the others. Thank you for your attention. If you'd like to delve deeper into the topic, I encourage you to explore the details by reading the paper.